All right, so let's go ahead and get in and finish our Chapter 1 stuff. And then we'll begin Section 2.1. I typed Myth Lab and it came up. So you can type a lot of different things. Let's go in and look at Chapter 1. This time I'm going to go in through the textbook rather than using the PowerPoint. I wanted to expose everybody to it, but from this point forward I'm just going to use the textbook. That way there's examples and stuff built in. And we'll do a couple examples which might answer some questions that you might have from the homework. And then after we finish, I'll ask and see if there's any other questions. Muggy in here, huh? Definitely. Hey. All right, so we left off in 1.5. Here's some review of the definitions that we talked about yesterday. So, of course, we talked about an experimental unit is an object about which we collect data. It can be anything, a person, a thing, a piece of sand, temperature outside, any number of things. You'll hear me call it observations. All right? A population is the set of these experimental units. So that's really where a lot of these questions from Chapter 1, you'll notice, the first thing it asks you is what's a population of interest, right? What are the objects that we are interested in studying? All right. And then in these objects, we have certain characteristics that we care about with which we call variables. A variable is a characteristic or property of an individual experimental unit within the population. So if we're talking about students in this class, our variable could be gender, height, weight, any other type of variable, whether it be qualitative or quantitative. Right? Just a review of that. And then a sample is a subset of the population. Right? It's a smaller piece. And it's a lot easier to come up with a sample because in order to get through the entire population, we have to do what's called a census. And as you guys know, just with the U.S. Census, it only happens once every 10 years. And I know the 2010 census was one of the most expensive public undertakings in the history of the United States. That's how expensive a census is. All right, so that's why we prefer to find a sample, a representative sample, and draw information from it. And then here was an example that we talked about on Monday. Voter ID, right? Our population is all registered voters. And then they had a sample of the first, second, and 1,500th voter ID cards. So there's a simple sample of our population. Then finally, we got to our definition of a statistical inference. A statistical inference is an estimate, prediction, or some other generalization about a population based on information contained in a sample. So we look at the sample, we pull information from it, and then we try to draw conclusions about the population as a whole. Right? We try to say, well, based on this sample, it had such and such characteristics, so then we believe that the population has those characteristics. All right? And I want to look at this asterisk thing down here. Let's talk about it. It says, the terms population and sample are often used to refer to the sets of measurements themselves, as well as to the units on which the measurements are made. When a single variable of interest is being measured, this usage causes little confusion. But when the terminology is ambiguous, which means it's hard to decipher, we'll refer to the measurements as population data sets and sample data sets, respectively. All right, when we're actually talking about the data that came from the population or from the sample. And your homework for 2.1, which we'll kind of get to today, you have to make some charts, right? You have to make some graphs based on some data sets that are given to you. All right, so population and sample basically talks about the units themselves, not necessarily the data that came from the units, which we'll call population data sets and sample data sets. All right, so review of what we talked about Tuesday. Let's look at an example right here. This is something we didn't do. We didn't have much time to do, and I know there's a few questions like this on your homework. So let's read through this. According to Variety, August 27, 2009, the average age of viewers of live television programs broadcast on CBS, NBC, and ABC, which is the three major networks, is 51 years. So that's the average age of viewers is 51 years old. Now that doesn't mean every viewer is 51, right? That means that's the average age. If I took every single viewer, added their ages together, and divided it by the number of viewers, that's what we come up with, right? 51 years of age. Suppose a rival network, i.e. Fox executive, hypothesizes that the average age of Fox viewers is less than 51. To test her hypothesis, she samples 200 Fox viewers and determines the age of each. First question says, describe the population. What is the population of interest? Who is the executive really worried about here? Right? From this sample, she's trying to draw conclusions about who. And then the solutions are right here, so this is a nice way to kind of lead into this. The population is the set of units of interest to the TV executive. The units of interest to the TV executive is every person that watches Fox News, right? Or Fox viewers. So that's what she's concerned with. She wants to know the average age of all Fox viewers. She's trying to do that by only taking a sample of 200 of the viewers. Now, you're probably thinking to yourself that you better be very careful in how you pick those 200 viewers, right? Or your data is going to be way off. You know, you don't want to go to, say, a retirement home and pick the viewers there, right? Because that's not a very representative sample. Okay, then it says describe the variable of interest. Who do they care about? Or what does she care about with these Fox viewers? And that's their average age. Right? She doesn't care about their income, where they live. Right? All she's concerned with right here is what is their average age. Right? The sample is the 200 viewers. So we see the difference in size of the population in the sample is probably huge, right? There's a big difference here in how many people actually watch the Fox channel as opposed to just the 200 people. Now, I mean, that's probably small if we even considered it just at Eastern, right? The 200 students. So this population is huge compared to the size of our sample. And you might be asking, well, how big does this sample have to be so that I can draw good conclusions from that population? That's something we'll get to, all right? Really depends on certain cases. I know on yesterday, on Monday, I said that about 1,500 is a good bar. That's where a lot of our, we're like Gallup polls and certain surveys goes up to about 1,500 people, even to draw conclusions about the population as a whole, right? Describe the inference. What is she trying to infer, right? The inference of interest involves the generalization of the information contained in the sample of 200 viewers to the population of Fox viewers. So she's going to take those 200 Fox viewers, find their average age, and then try to generalize the average age of all Fox viewers. Now, if this 200 people was chosen in a good manner, she's going to come up with a pretty good result. If it's chosen in a bad manner, her data is probably not going to be very good. Remember I mentioned yesterday, bad data is worse than no data, right? So you want to make sure that you're picking these 200 viewers in a good manner. And we'll talk about how to do that, all right? In particular, the executive wants to estimate the average age of the viewers in order to determine whether it is less than 51 years, right? Because that's what she claimed up here. To test her hypothesis, she samples 200 viewers and determines the age of each. Right? She might accomplish this by calculating the average age of the sample and using that average to estimate the average age of the population. All right, so there's an example. This is something that you'll see on your homework, right? There's 3 or 4 questions about this right here from chapter 1. Okay? All right, let's move on. And here's another Cola Wars example. If you need a little more practice, you can come through the textbook and read this. This appears on page 7 of the textbook. All right, so you go in there and click page 7, and it'll pull this example up. Okay. We talked about measures of reliability, right, which is kind of like that plus-minus scale you see with polls, right? The margin of error is kind of another way to think about it. Right? How good is our estimate? Is a way to think about measure of reliability. Is it a good estimate or is it a bad estimate? The measure of reliability that accompanies an inference separates the science of statistics from the art of fortune telling. Right? So if it's reliable, it becomes science. If it's unreliable, it becomes fortune telling. Right? That's what this is talking about here. A palm reader, like a statistician, may examine a sample, which is your hand, right? And make an inference about the population, which is your life. Well, it says, well, your lifeline is this long, you're going to be 75 years old. Now, that's fortune telling, right? There's no science to back that up. However, unlike statistical inferences, the palm reader's inferences include no measure of reliability, right? She could be correct from anywhere to 0 to 100%. That's not very reliable. And that's what measure of reliability is talking about. Is a statement, of course, it's usually quantitative, which means it's numerical in value, right? The plus minus 5% or whatever it happens to be, about the degree of uncertainty associated with a statistical inference. All right. And we'll talk about how to create this type of stuff as the summer goes on. So still more review, right? We talked about this stuff Monday. And then we got to this point, 4 elements of descriptive statistical problems. Notice 1 and 2 are the same for both cases. First, we need to know the population or sample of interest, and we need to know a variable, right? Who do we care about, and what do we care about? That's what's important, whether it's descriptive or inferential. Descriptive, which is what we're going to mess with today in 2.1, is we're going to create some tables, graphs, or some other numerical summary tools so that we can describe this data, all right? So that we can look at it and be able to tell what the data is telling us, right? And then finally, identify some patterns. So you'll notice in inferential, we still have our population of interest, our variables to be investigated, the sample of population units, and then the inference about the population based on information contained in the sample, which is what the Fox executive was trying to do, right? Based on her 200 sample, that average age, she was trying to infer what the average age of all Fox viewers were. And that example didn't have anything with a measure of reliability. We need to know how that executive created those 200 people, right? How did she come up with that sample in order to tell what a measure of reliability would be? Then it didn't even give us any data, right? It just basically went over the problem. Okay. So there's Pepsi versus Cola, and see here, let's read over this. This is the Pepsi Cola problem that I kind of glanced over and said if you want to, you can go back and read it. But what we're going to do is I want to mention this right here. The interval 56 plus or minus 5 is called a confidence interval. See, does everybody notice that plus or minus 5, right, from the polling? Plus or minus 5%, plus or minus 3%. Since we are confident that the true percentage of cola customers who prefer Pepsi in a taste test falls into the range 51 to 61 because the average was 56. So it's 56 with 5 higher or 56 with 5 lower. That's what's called a confidence interval. Is anybody in here taking 106? Math 106 here on campus? Yeah? We talk about confidence intervals in there, right? No, there's not much context to them, but we do spend time creating them. And you'll see them a lot more in this class, all right? And if, I could go through this class and say, what do you like better, Pepsi or Coke? But actually, I don't know if you guys know this, but the percentage of Coke drinkers in general has been on the decline over the last 4 years. especially as the population has went up, right? So that's pretty significant, which is good because that high fructose corn syrup is not very healthy. What's my measure of reliability on that? I mean, there's clinical trials done on that all the time. If you're interested, you can go look online on that stuff. Okay, now we have 1.4 types of data. There's two types of data. One is quantitative. The way, you guys, I want you to remember that is this letter N right here. Yeah, this one doesn't have the N. It's qualitative. So quantitative deals with numbers, right? Quantitative data are data that are measured on a naturally occurring numerical scale. The following are examples of quantitative data. The temperature in degrees Celsius at which each piece in a sample of 20 pieces of heat-resistant plastic begins to melt. Right? What is the melt temperature? Is what this is saying. That is a quantitative data. Right? And there's lots of examples of this on your homework. Here's some other types of quantitative data. The current unemployment rate, right, is always given to us in a number, basically a percentage. The unemployment rate is the percentage of people at work age that aren't working. Right? That's kind of how they come up with that number. Well, that's how they describe that number. How they come up with that number is a whole nother. I mean, we could spend a whole semester just talking about that. That's how significant, you know, how much goes into it. The score of a sample of 150 law school applicants, right? When you guys took your ACT and SAT, that's a quantitative data. Right? Number of convicted murderers who received the death penalty. And conversely, data can also be what's called qualitative, which is this example. In contrast, qualitative data cannot be measured on a natural numerical scale. Eye color, right? Favorite color. I mean, we can come up with thousands of examples. What's your favorite barbecue sauce? Right? That is qualitative data. Right? And we'll see today that qualitative and quantitative data, we kind of describe them in different ways when we go to graph them, okay, and look at them. There's different ways in which we display this stuff. The size of a car, right? Subcompact, compact, mid-size, or full size. Defective or not. Yes or no is a qualitative data, right? Yes or no. Qualitative are measurements that cannot be measured on a natural numerical scale. Types of fish in a river, right? This DDT, this is in your homework, you have to create some charts from this data right here, right? So as we look through it, through these 5 examples, you could probably identify pretty quickly which one's qualitative and which one's quantitative. Which ones are qualitative, which ones are quantitative. The species, of course, would be a qualitative data, right? River Creek where fish was captured would be qualitative, right? You notice that both of these include units, and so does this one, parts per million. All 3 of those would be numerical in nature, right? So this all review. Stuff we talked about Monday. Here's the new stuff. So let's jump in here. Now this is ways to collect data, right? There's 3 types of ways that this book describes to collect data, okay? Once you decide on the type of data, whether it's quantitative or qualitative, right? Is it a number or is it non-numerical? Is appropriate for the problem at hand, you'll need to collect the data. So you got to go in and actually get it, right? Generally, you can obtain data in 3 different ways. First is let somebody else do the work, right? A published source. Go and look at something that's already out, where they went through and collected the data. Of course, you want that source to be reputable, right? You don't want to just Google something on the internet and click the first thing you see, all right? You want to do a little background investigation. Sometimes the data set of interest has already been collected for you and is available in a published source. In your homework for 2.1, that's what I'm giving you is some published data, some stuff that's already there, okay? Such as a book, journal, or newspaper, right? For example, you may want to examine and summarize the divorce rates in the 50 states of the United States. You can find this data set as well as numerous other data sets at your library in the Statistical Abstract of the United States, published annually by the U.S. government. Right? Similarly, someone who is interested in monthly mortgage applications would go to the Survey of Current Business. Right? How many houses are being sold in a given month? Economists really care about that type of stuff, right? That kind of tells how the economy's doing. All right. Other examples of published data sources include the Wall Street Journal, the Sporting News, and of course the Internet, which you have to really pay attention to, right? Because there's a lot of fluff out there. Okay. Or we can go and get the data in what's called a designed experiment. All right? A designed experiment in which the researcher exerts strict control over the units in the study, right? The observational units, whether they're people, objects, or things. For example, an Austin-cited medical study investigated the potential of aspirin in preventing heart attacks. Right, you guys have all heard that, right? Bayer aspirin will decrease your chances of getting a heart attack. Volunteer physicians were divided into two groups, the treatment and the control group. Something you guys have probably heard of before, right? In your science classes, whenever you do an experiment, you try to hold everything the same except the variable you're worried about, right? Each physician in the treatment group took one aspirin tablet a day for 1 year, while each physician in the control group took an aspirin-free placebo. We have to give those people a placebo because we have to make them think that they're getting aspirin. Because if they don't think they're getting aspirin, they actually won't get better. There's actually studies that show if you think you're getting better, if you think you're getting the drug, it produces positive effects. That is the placebo effect, which is really amazing when you sit back and think about it. You know, the whole subject of psychology really could be based around this placebo effect, right? The fact that your brain, what you think, really makes a big, really makes a lot into what happens to you, right? The researchers, not the physicians under study, controlled who received the aspirin. Of course, the physicians couldn't know if they were getting a placebo because that makes it worthless. Right? What good is it if they know it's a water pill? All right, and who received the placebo? As you'll learn in Chapter 10, which is down the road, a properly designed experiment allows you to extract more information from the data than is possible with an uncontrolled study. Because if our study isn't controlled, then we lose reliability. Right? Then our data that we get isn't very reliable. That's why we really need a control group so that it can be reliable. So we could say everything's the same except for some of the physicians took aspirin. And as we'll see, there's a lot of other stuff that we call confounding variables that play into this. I mean, what if these physicians that were taking aspirin happen to be more active, right, and exercise more? That could have some influence on it. So you want to make sure these two groups, your control group and your treatment group, exercise the same amount, basically eat the same types of food, right? They're exactly the same in every aspect except for the fact that one's getting an aspirin and one's getting a placebo. All right? And then finally, the last one, observational studies can be employed to collect data. In an observational study, the researcher observes the experimental units in their natural setting and records the variables of interest. This happens a lot in nature. Right, the one lady, I can't remember her name off the top of my head, where she'd go out and watch gorillas to see how their habits were, right? That would be an observational study. Somebody sits back and just observes. They have no active involvement in the study, which is the difference between a designed experiment, where the researchers do have an active involvement. Right? They actually pick who goes in the control group and who goes in the treatment group. Okay? So as you look at these, the easiest would be getting data from somewhere else. Right? Let somebody else do the work. Then an observational study is where you just kind of sit back and watch. It might take time, but it doesn't take a lot of effort. And then finally, a designed experiment takes time and effort, right? But as we'll see, the designed experiment is a good way to get really reliable results as long as it's designed correctly. And that's how drugs hit the market, is going through this type of stuff, right? Pfizer and Merck, all those type of pharmaceutical companies. Right? They don't just give people pills and observe. They actually do a designed experiment. Okay? Ooh. With published data, we often make a distinction between the primary source and a secondary source, i.e. the New York Times and then Wikipedia, right, would be a secondary source. If the publisher is the original collector of the data, the source is primary. Otherwise, the data is secondary source data. And just like the game of telephone, right, the more people that it goes through, it might happen to change the data a little bit. So you always want to get it from the primary source if possible. All right? Okay. So let's go back and give you a nice, a nice definition of this stuff. So the most common type of observational study, let's look up there, is a survey. A survey is an observational study. Somebody goes around and asks you questions, where the researcher samples a group of people, asks one or more questions, and records the responses. Right? They're not trying to sway them one way or another. But something that can happen is the way a question is asked can sway the answer. Or you can say, well, are you for the killing of baby dolphins in the ocean? Of course nobody's going to say yes to that, right? But it might be having some effect on the ecosystem there. So the way you ask the question makes a big difference in what type of data you get. Right? Probably the most familiar type of survey is the political poll, conducted by Harris, Gallup, Roper, CNN, all these different polls, and designed to predict the outcome of a public election, of a political election from the public. Another familiar survey is the Nielsen survey, which tells you the ratings, right? Nielsen ratings. So advertisers are really concerned with those, right? Because if there's a lot of people watching a certain program, they want to get their commercials on there, right? Because then more eyes get to see it. All right? Surveys can be conducted through the mail, which usually isn't very good because you see the thing in the mail, you usually think it's junk mail, and it goes in the circular filing cabinet, right? You just throw it away. So what people do is they actually call on a telephone, right? Because people are more accepting of answering a question from a person than from a piece of paper, right? So that's why surveys are done that way. Okay, here's the definition of a designed experiment. It's a data collection method where the researcher exerts full control. That's a lot different than a observational study, right? There the researcher just kind of sits back and watches. A designed experiment is a data collection method where the researcher exerts full control over the characteristics of the experimental units sampled. These experiments typically involve a group of experimental units that are assigned to the treatment and control group. You know, we need the control group for kind of a basis. All right. So design experiments are good, but they take time and they cost money. So that's why you don't just do that all the time, right? You know, if they were cheap and easy and you could get reliable data from that, then that's all that we would do. But they're not. And then finally, an observational study is a data collection method where the experimental units are sampled, are observed in their natural setting. No attempt is made to control the characteristics, as opposed to a designed experiment where the researcher exerts full control over the characteristics. Okay? Any questions over those two? It's just ways of collecting data. And as you sit back and look at this, you know, this data would probably be more reliable than the observational, right? Because if somebody's going and asking questions, the person can lie, right? Maybe you want to stick them on a lie detector, but then you're almost doing a designed experiment in that case. Okay. Now let's get to a definition that really is important. This next definition really leads to how reliable our data is going to be. Right? If we want to make our data reliable from a sample, if we want to make good inferences about a population, we have to make sure that our sample is what's called representative. Regardless of which data collection method is employed, it is likely that the data will be a sample from some population. If we wish to apply inferential statistics, we must obtain a representative sample. That is an absolute must. So back to the example of the Fox viewers. You know, the executive wants to make sure that she's just not going to a retirement home, because that's not very representative of all the people watching Fox. Right? There's young people, older people, middle-aged people. So if you want to get a good sample, you need people in all those age groups. A representative sample exhibits characteristics typical of those possessed by the target population. So here at Eastern, the male-female ratio is about 60-40, give or take. All right, and in here today, we have 7 people, 3 are male, so that's pretty close as far as gender. So this class, just the 7 people sitting in here, is pretty representative, is typical of the male-female ratio of the entire student body. So that would be representative in that sense. But we would need to look at more characteristics than just gender. I mean, we need to look at age and a lot of different things. You know, and a lot of questions are, you know, where do you stop? Right? We want to make sure that you're all from, you know, the same proportion of students from in New Mexico and out of New Mexico, the same percentage of students that are veterans and aren't veterans. Right? So, you know, that's kind of the hard part with creating a representative sample is where do you stop imposing the characteristics? And as we'll see, basically, the best way to create a representative sample is by simple random selection. Remove humans. Humans cannot be picking the sample. It has to be some other means, some other random selection. That's why at the beginning of a football game, what do? They flip a coin. Right? That's random. Okay. And then here we go. For example, consider a political poll conducting during a presidential election year. Assume that the pollster wants to estimate the percentage of all 145 million registered voters in the United States who favor the incumbent president. Now, you don't want to survey every single one of these people. I mean, that would be a census. That would take forever. Right? Costs a lot of money. And then the people might lie to you anyways. The pollster would be unwise to base the estimate on a survey data collected for a sample of voters from the incumbent's own state. Right? Of course. Makes sense. Because those people are going to be more biased to vote for the incumbent president. Right. Such an estimate would almost certainly be biased high. There's that word biased. Let me zoom this in a little bit more. So I kind of want to get it all on one page. There we go. Is that a little better? Okay. So we don't want biased samples. The best way to remove this word, that's the bad word of statistics. All right? You know, you guys have grown up hearing 4-letter words are bad. Biased is the bad word in sampling. Right? You want to stay away from that. The most common way to satisfy the representative sample requirements is to select a random sample. What's a big example of random? You know, giving something away at random. You know, when you drive by the convenience store, the Powerball lottery, right? That is completely, well, it's supposed to be random. I mean, you don't really see it on the back end. Now, who knows, maybe somebody's getting a kickback, but it's supposed to be random, right? Like bingo. Put all the balls in a basket, you spin the basket around, and you draw one out, right? That's random. Now, the person doing the drawing makes sure that they don't look in there, right? Because that would bias the sample. So really the best way to remove bias is to remove human selection, right? People cannot be the ones making the pick. A random sample ensures that every subset of fixed size in the population has the same chance of being included in the sample. If the pollster samples 1,500 of the 145 million voters in the population, so that every subset of 1,500 voters has an equal chance of being selected. Now, how many different subsets of 1,500 voters is there in 145 million? A lot, right? Millions and millions, right? And there's actually mathematical ways to determine how many different samples we could make. And we'll see that later on in the semester, or in the summer. Okay? The procedure for selecting a random sample is discussed in Chapter 3. Here we will look at 2 examples involving actual sampling studies. A random sample of n experimental units is a sample selected from the population in such a way that every different sample size n has an equal chance of selection. That's your definition of random. For something to be random, every member in the population has to have an equal chance of being selected. Just like the bingo balls, right? Every ball in the basket has an equal chance of being selected. Dice is another random, right? Is another random roll. That's why if you ever see in the casino, if like a die gets thrown off the table, they always weigh it, right? They want to make sure that it's not biased, right? They want to make sure that each side is just as likely to come up as any of the other sides. So that's a good way to think about randomness. Because if I rolled a 6-sided die 6,000 times, roughly I'd have 1,000 ones, 1,000 twos, 1,000 threes, 1,000 fours, 1,000 fives, and 1,000 sixes. Right? Not exactly, but pretty close. And the more times I roll it, the more and more of those samples would become equal. Right? The number of times those things would show up. And that's something you guys do in 106, right? You do a lot of that dice rolling stuff. All right? In statistical sampling theory, the sample is better known as simple random sample. A simple random sample is where you put all the members of the population in a hat and draw out. There's actually a way to improve that a little bit by breaking it down into what's called strata and then randomly selecting. But it really, in the long run, it doesn't have much of an effect. All right. So let's read this. What percentage of web users are addicted to the internet? Now, this number probably goes up as time goes on, right? Because more and more people have the ability to get to the internet. To find out, a psychologist designed a series of 10 questions based on a widely used set of criteria for gambling addiction and distributed them through the website abcnews.com. So that's something to think about, right? A sample question: do you use the internet to escape problems? A total of 17,251 web users responded to the questionnaire. If participants answered yes to at least half of the questions, they were viewed as addicted. The findings released at an annual meeting of the American Psychological Association revealed that 990 respondents, or 5.7%, are addicted to the internet. Right? Identify the data collection method. Are they going in and imposing who answers this question, or are they just basically sitting back and watching? What do you guys think? Sitting back, right? The data collection method is a survey. Because the users got to determine if they responded or not. Right? So that would be a observational. B, identify the target population. Who are they trying to draw inferences about? Basically, all internet users, right? Of every person that uses the internet, how many are addicted to it? Since the website can be accessed by anyone surfing the internet, presumably the target population is all internet users, young and old. All right. Are the sample data representative of the population? What do you guys think? What's your inclination? You're probably not going to be on the internet. Yeah. Right? Yeah. If you're not addicted to the internet, you're probably not going to be on here, so you're probably not even going to see it to begin with. Right? Or what if you only get on it to pay your bills, right? Or only to do a few things. So let's read what it says. Because the 17,251 respondents clearly make up a subset of the target population, they are a sample. That's definitely a sample. But we're asking, is it representative of the population? Whether or not the sample is representative is kind of unclear. I would probably say, I would agree with Crystal that I'd say no. And mainly because of this. The respondents are self-selection. They decide whether they're going to be in it or not. Right? It's not like the internet went out and did a random question to only a few internet users. Right? That question went out to every internet user. And the internet user had to say, yeah, I'm going to go ahead and answer the question. A lot of times you'll see on websites, you'll be reading an article, and what will happen? A survey window will pop up, right? Would you like to take a survey? 9 out of 10 of us, what do we hit? No thanks, right? So we have removed ourselves from the study. That type of survey suffers from what's called non-response bias. People didn't respond to the survey, right? And, people don't want to call themselves addicted to the internet. So even if you were, you'd probably lie a little bit to this, right? I.e., each internet user who saw the survey chose whether or not to respond to it suffers from non-response bias. It is possible that many internet users who chose not to respond would have answered questions differently, leading to a higher percentage of affirmative answers. Basically, any inferences based on survey samples that employ self-selection are suspect due to potential non-response bias. So really, we couldn't use this data. We couldn't really infer from this. Our reliability of this data is not very high. That's what we get out of this. All right, there's some more examples if you want to read through. This is on page 13. I think that's about it. Okay. Role of statistics in critical thinking and ethics. Exactly which one I wanted to cover in here. And let's look at this example to do it. Let's read this H.G. Wells thing, just kind of get an idea of what it's talking about. English-born Herbert George Wells published his first novel, The Time Machine, in 1895 as a parody of the English class diversion and a satirical warning that human progress is inevitable. Although most famous as a science fiction novelist, you guys might remember him from, he did the thing on the radio where the aliens were coming and people thought it was real, right? Yeah, I can't remember what the name of it was exactly.
War of the Worlds.
Yeah, that's what it was.
Orson Welles, actually.
Orson Welles, okay.
But it was using H.G. Wells' story.
That's what it was, right. Yeah, and they were related, aren't they? I think. Okay. Although most famous as science fiction novelist, Wells was as prolific a writer as a journalist, sociologist, historian, and philosopher. Wells' prediction about statistical thinking is just one of a plethora of observations he made about life on this world. Here are a few more of H.G. Wells' more famous quotes. Advertising is legalized lying. Sometimes yes, right? Depends on who your target market is. Right? Crude classification and false generalizations are the curse of organized life. Right? When we try to make an inference based on data that was not collected in a good manner, that's what happens. We make false generalizations. Right? The crisis of today is the joke of tomorrow. Just kind of like the War of the Worlds thing. Right? Now it's a joke, basically. Back then it wasn't a joke. Right? Fools make researchers and wise men exploit them. That one you can kind of read to your own. All right. Statistical thinking. What is statistical thinking? Involves applying rational thought and the science of statistics to critically assess data and inferences. Rational thought, which as we look out in the world, maybe that doesn't happen nearly as much as it should, right? Fundamental to the thought process is that variation exists in populations of data. Which what that leads us to believe is, if I'm going to take a random sample from a population, the fact that it's a sample leads to the fact that there is going to be some variation. There's nothing we can do about it. All right? We can try and minimize it, but we can't get rid of it. That's another thing that we call a chance bias. All right? Or chance error. Excuse me, not bias. Chance error. The fact that it's just a sample could produce different results. To gain some insight into the role statistics plays in critical thinking, we present two examples of some misleading or faulty surveys. So this statistical thinking really backs up. Remember on Monday I said, you go into your boss and you say, hey, I want a raise. Well, you need some statistical thinking to back up your statement. Why do you need a raise? Show me some numbers. Show me some data. That's what this is talking about. An article in the New York Times considered the question of whether motorcyclists should be required by law to wear helmets. We all are required by law to wear seatbelts, right? So I would think a helmet is a little more important than a seatbelt. But in supporting his argument for no helmets, the editor of a magazine for Harley-Davidson, so it's the editor from Harley-Davidson. So is he biased? Probably, right? One way or the other. I mean, most people that wear Harleys or ride Harleys, there's not a lot of helmets, right? Okay. Bikers presented the results of one study that claimed 9 states without helmet laws had a lower fatality rate than those that mandated helmets. A survey that found of 2,500 bikers at a rally, 98% of the respondents opposed such laws. Now think about where that sample came from. I mean, if these are bikers at a rally, You know, they probably believe one way or the other, right? More than likely against wearing helmets, right? If you're asking the parents of these bikers, what are they probably going to say? That they need to wear helmets, right? What further statistical information would you like? Okay, based on this information, do you think it's safer to ride a motorcycle without a helmet? Of course not. I mean, that's you know, that would be completely far-fetched to say yes. I mean, how could wearing safety equipment make you less safe? Right? You can use statistical thinking to help you critically evaluate the study. For example, before you evaluate the validity of the 98% estimate, you would want to know how the data were collected. Of course, right? You want to know where it comes from. If a survey was in fact conducted, it's possible that the 2,500 bikers in the sample were not selected at random. Doesn't sound like it. You know, they probably had a sign up that said, "Are you for or against helmets?" So people that feel strongly one way or the other are going to come answer that survey. People that don't care are just going to walk by it, right? If the respondents were likely to have strong opinions regarding the helmet law, the resulting estimate is probably biased high. Also, if the biased sample was intentional with the sole purpose to mislead the public, the researchers would be guilty of unethical statistical practice, right? If they were set up to purposely mislead the public. And there's a lot of examples of this in movies, right, where they try to skew the data to purposely mislead. And there's lots of examples of that. You would also want more information about the study comparing the motorcycle fatality rates of the 9 states without a helmet law to those states that mandate helmets. Now, what I would say is the states that mandate helmets probably have a lot more people on the road riding motorcycles. So their chances of more wrecks is higher. So, of course, there's going to be more people that have a fatal accident from that, right? If you go to Montana where there's 10 people riding a motorcycle, right, it changes what happens with your data. All right? Were all 50 states included in the study, or were only certain states selected? Probably only certain states. That is, are you seeing the sample data or population data? Furthermore, do the helmet laws vary among states? If so, can you really compare the fatality rates? So that would be an unethical statistical practice. That person probably went in, well, definitely went in. He was the owner of Harley Davidson. He went in and tried to purposely mislead the public with the data. All right? And this is when talking about Howard Stern when he moved his radio show from over-the-air to Sirius satellite radio, which you have to pay for a subscription, right? It's not free access over the air. That's something you guys can read. All right. And then now here's some nice definitions of the words we've already talked about. As with many statistical studies, both the motorcycle helmet study and the satellite ratio study, which we didn't go over, are based on survey data. Most of the problems with these surveys result from the use of non-random samples. Randomness is the cornerstone to creating a good sample. You have to select at random. These samples are subject to errors such as selection bias, non-response bias, and measurement error. Or they might just measure it wrong. Researchers who are aware of these problems, yet still try to push the data on you, are doing unethical statistics. Right? Another unethical type thing is insider trading. Right? That's why it's against the law. Because you go in and kind of see what's going on the back end, and then you try and exploit that. Selection bias results when a subset of experimental units is excluded, purposely excluded from the sample. That's selection bias. Usually, if humans are involved in making selection, there's selection bias. There's nothing we can do about it. Humans are inherently biased. Right? If I was one asking these bikers, maybe there was one that was really scary looking, so I walked by him. Right? I didn't want to know what his opinion was. I biased that study by my own selection. It wasn't random. Non-response bias results when the researchers conducting a survey or study are unable to obtain all data on all experimental units selected for the sample. This happens a lot when surveys are mailed out, the stuff online, right, on the internet, when the thing pops up. Those definitely suffer from non-response bias. And then finally, measurement error. Refers to inaccuracies in the values of the data recorded. In surveys, this kind of error may be due to ambiguous or leading questions. A leading question is like what I said about the dolphins. That's a leading question. Are you for or against killing baby dolphins in the ocean? Right? Even though they might be destroying some really pristine ecosystem. Right? And dolphins can survive everywhere, but this ecosystem they're destroying only exists in one place. So really, for the good of the whole, maybe you do want to get rid of those dolphins, right? But that question leads you to think that you don't want to. Once again, people are the ones making the problems here, right? Humans are biased in this stuff. And the interviewer's effect on the respondent. And another thing that's been shown, because I talk about this a lot in another one of my math classes, women are more likely to give true answers to women, men are more likely to give true answers to men. That's just the way it is. It's been proven. All right, so I'll leave this up for another minute so you get these. So, chapter 1 is chock full of definitions. All right, we've probably done about 25 of them. So lots of definitions, lots of words that we need to understand so that we can take the next step. Right, you got to know the alphabet before you can read and write. That's what we're learning. We're learning the statistical alphabet here. So now in the future, when I say this type of stuff, what's the population of interest, we'll know what I'm talking about. All right? Was there questions on the homework? Did anybody come across a question they couldn't quite figure out for chapter 1? No? Okay. All right, let's get to the next. What does 2.1 start? 25. Okay. So now let's get away from these definitions and start actually putting some data down on paper. So the first section, I think at the beginning of class I said the quantitative was first. We talked about qualitative first and then quantitative. So that's what we're going to finish out with today. We'll do this section. Describing qualitative data. There's 3 main ways to describe qualitative data that we're going to talk about in here. Right? 2 of them are similar. It's just basically the way the stuff is arranged. And then one of them is really difficult to draw, which we'll see. Right? So where we've been, what have we done up to this point? We've examined the difference between inferential and descriptive statistics. Inferential is where we're trying to make an assumption on the entire population based on a sample. Descriptive is where we're just simply writing down what we've observed, right? What's happened. We're not trying to make any inferences. Describes the key elements of a statistical problem. Learn the 2 types of data, quantitative, which is numerical, and qualitative, which is non-numerical. And discuss the role of statistical thinking in managerial decision making. Right? When a manager makes a decision, they want some data to back that up. Right? They can't just point their finger and say you. Right? They really want to have some data behind it. Where we're going, we're going to describe qualitative data with graphs, and then we'll describe quantitative data with graphs. Then we'll describe quantitative data with numerical measures, and describe the relationship between 2 quantitative variables with a graph. Right? Okay. So this is an example. It's pretty interesting. If you have some time, you can go in and read it. It's talking about body image dissatisfaction. Is it real or imagined? Right? How do they actually come up with this? Are you dissatisfied with your body image? That's what this is talking about. All right. Okay. Let's get to 2.1. All right. Describing qualitative data. Consider a study of aphasia published in the Journal of Communicative Disorders. Anybody know what aphasia is? You know, some people in here are ComDis majors, right? So I got to take this stats class. Aphasia is the impairment or loss of the faculty of using or understanding spoken or written language. So you did know how to read and write? Or spoken and written? Yeah, read and write. And now you don't. That's aphasia. And I think I'm pronouncing it right. 3 types of aphasia have been identified by researchers. Broca's, conduction, and anomic. That's 3 different types. Those words were put together by some communicative disorders people, right? Broca's looks like it's somebody's name, right? That's why it's capital. The researchers wanted to determine whether one type of aphasia occurs more often than any other, right? Is Broca's more likely than the other 2? Or is anomic more likely than the other 2? Or is conduction more likely, right? Consequently, they measured the type of aphasia for a sample of 22 adult aphases, which means that the people already had to have aphasia, right? Of course, if they don't have aphasia, they weren't a candidate for this study. So their what's their target population here? What are they trying to draw conclusions about? What do you guys think? From this sample of 22. All people with aphasia, right? Any person that suffers from aphasia. All right? Table 2.1 gives the type of aphasia diagnosed, which we'll see. For this study, the variable of interest type of aphasia is qualitative, right? It's not a number. It's non-numerical. Thus, the value of qualitative variables can only be classified into categories called classes. The possible types of aphasia, Broca's, conduction, and anomic, represent the classes for this qualitative variable. So we have 3 classes here. We can summarize such data numerically in 2 ways. By computing the class frequency. So frequency means how often it appears, right? How frequent is it? The number of observations in the data set that falls into each class, or one that actually tells us a relative stance, which is something Dr. Gamble really likes to do. You know, if you ever go and listen to him do a talk, you know, he might give you some data, some numbers, but he doesn't just like throwing out numbers, right? He likes to say compared to what, right? You might hear that ENMU lost $1 million in funding, which might sound like a lot of money, but when compared to the total amount, it might not be that much. That's the difference between frequency and relative frequency, all right? Or total revenue from taxes was $1 billion more than last year, which sounds like a lot of money, but when you consider it as a percentage of all the tax revenue, it's really minute. All right? That's the difference between frequency and relative frequency. So frequency is the number of observations in the data set, and the relative frequency is the proportion of the total number of observations. All right? Which, another way to think about relative frequency is percentage. But relative frequency is the decimal form of the percentage, right? That's why we like using percentages so much, because it kind of gives us a basis, right? It compares it, all right? So a class, first definition, a class is one of the categories into which qualitative data can be classified, all right? And the number of classes depends on what type of data you're collecting, right? Class is one of the categories into which qualitative data can be classified. The class frequency is the number of observations in the data set that falls into a particular class, right? And then the class relative frequency is basically divided by n. How many times it appeared divided by the total number, right? The class relative frequency is the class frequency divided by the total number of observations in the data set. For this aphasia, how many observations are there? Up there, right? 22. There's 22 different observations. So I need to determine how many fall in each category and then divide it by 22 to get the frequency. Right? And then move the decimal over twice to get the percentage. Okay? Okay. So relative is a much stronger thing. Because it doesn't make sense to say, well, 8 people suffered from Broca's. It makes a lot more sense to say, well, 0.25 relative frequency, or 25% of the people. The actual number doesn't really mean anything. All right. I'll leave that up there for another minute. So this word relative really is important. How is it relative to all the other classes? All right, now let's look at our actual data here. This is something you'll see on your homework, right? You'll pull up a data set just like this. There's a data set. Now, not this specific one, but something similar. So here's our data set. Rather than give them a name, they give them a number to protect anonymity or to lead to less bias. Now, you might be thinking, well, wouldn't you want to separate this into male and female? Maybe one happens to show up more in males than in females. Or maybe that's something you'd want to do later on. Okay? So here it is, of the 22 subjects. Now, just glancing at that, it's hard to tell which one occurs the most. It's kind of easy to see which one occurs the least. Looks like Broca's isn't up there very much. But isn't up there very much is not a very statistical statement. Right? We want to actually attach a value to it so that we can have more reliability rather than just say, well, it looks like. That's not very statistical. All right? So the class percentage is just the relative frequency with the decimal moved over twice, right, to create a percentage. The percentage symbol means divided by 100. Right? So to come up with the percentage, we take the frequency and multiply it by 100. All right? Okay. So the actual math here isn't anything over the top. It's just attaching the different words to it is the new stuff. Right? You know, you guys do this relative frequency stuff all the time, right? When you're paying your bills, right? What percentage of your total income is your mortgage, right? That's the type of stuff you need to worry about, which is the same type of thing. We just don't attach these fancy words of frequency, relative frequency to it. So, examining table 2.1, so they took that previous table and they actually start making marks. How many times did anomic show up? Well, it showed up 10 times. How did they come up with this percent? Well, they take 10 and divide it by 22. So that means 45.5% of all the observations suffered from anomic asphasia. I couldn't tell you what the difference between these three things are. That's not really important, right? It's just categorizing them. Broca's does show up the least, which confirms my assumption, right, by looking at the data. Well, it looked like Broca's didn't show up the most, didn't show up as much, and as I go in and examine the data, it didn't. It showed up less than 1/4 of the time, 22.7%. So by looking at this, if that sample was drawn in a good manner, all right, if it wasn't biased to where the researcher picked people that they thought were anomic, right? If they were randomly selected from a group of people suffering from asphasia, I would say that your greatest chances is having this anomic asphasia. So if I was to randomly select one person from the population of all asphasia sufferers, they're most likely going to be anomic. You guys see that? But even more than that, they're more likely to be one of these two more than anomic, right? Because when you add those two together, it becomes more than this, right? It's 54.5. This cumulative percentage, all they're doing is adding together these percentages. So 45.5 plus 22.7 is 68.2. Now, where do you guys hear this word cumulative a lot in college? When you take what test? Your final exam for any class, right? They always say it's cumulative. It's everything over the semester. It's not just the last chapter. That's what cumulative means. It's everything put together. And of course, when you add together all these percentages, it better be 100, right? You can't have more or less than 100% when you add them all together. Okay? Now, looking at this chart is one way to look at this data. But there's other ways that we can describe and show this data. Okay? Figure 2.1 also gives the relative frequency of each of the three aphasia classes. So in the class relative frequency definition, we calculate the relative frequency by dividing the class frequency by the total number. So you notice this 0.455 is just like this number with a decimal moved over twice or multiplied by 100. So it's very important that this is categorized as percent so that I know it's a decimal. Right? Thus, the relative frequencies of the three types of aphasia are. So you notice the difference between the relative frequency and the percentage is just the fact of where the decimal's at, right? So when I add together all these, what am I going to come up with? 100 or these three added together will be 100? 1. There'll be 1. So when you add together your relative frequencies, you should come up with 1. When you add together your percentages, you should get 100. Okay? In baseball, your batting average, right? When you see somebody's batting average, it's a relative frequency, right? It's a decimal. It's the total number of hits divided by the total number of at-bats. So if somebody has a 300 batting average, a .300, that means they hit 30% of the time. Right? 30% of their at-bats, they get a hit. That's what that means. Okay? So a batting average is just a relative frequency. But then you see in basketball, they have a free throw percentage, right? They don't tell you the decimal, they give you the percentage. But it's the same thing. The number of made free throws divided by the total number taken. Right? So we see the similarities between those two things. Okay, now let's look at a way to describe this data. These values expressed as a percent are shown in the SPSS summary table of figure 2.1. From these relative frequencies, we observed that nearly half, 45.5%, which is nearly half of the 22 subjects, are suffering from anomic aphasia. Anomic aphasia, excuse me. Although the summary table of figure 2.1 adequately describes the data, we often want a graphical presentation. Because this just isn't as pretty. Right? In a newspaper, you don't really see the data described this way. You see a nice pretty chart with colors and numbers, right? Where it's a little easier to identify the highest number. And a bar chart is simply that. You basically create bars. Notice this bar goes up to 10, because that's how many people suffered from anomic aphasia. And we have 5 for Broca's and 7 for conduction. You could create a pie chart. Now, pie charts are kind of hard to create by hand. Because how do you get exactly a slice that's exactly 31.8% without using a protractor, basically? Right? Is the only way to accurately do it. You know, we can kind of put it on there, but drawing a circle, you know, it is impossible, actually, for a human to draw a perfect circle freehand. Do you guys know that? No matter what, it won't be exactly a circle. You know, there's lots of ways to get around it. If you ever watch Bob Ross, he has a cool technique for creating a perfect circle. And it's just using the brush, so it's not even really doing it full hand, or freehand. So here's 2 types of data displaying. 2 types of ways to display data, a bar chart and a pie chart. Now I could change this frequency bar chart to a relative frequency bar chart. And it doesn't have anything, it doesn't change this axis, which I'll call the x-axis for clarity, right? The horizontal axis. So this won't change at all. But what's going to happen to these numbers over here? So let's see if we can draw a relative frequency bar chart. So down here is still my type, which I'll call A for short, B and C. And rather than be frequency over here, it's going to be relative frequency. What was it for A? You guys remember?
0.455.
Yep. So right there would be 0.455. That's the relative frequency of anomic. What was Broca's? Which I mean, is 0.22, wasn't it? 0.227. And then 0.318. 0.227. And then Notice I just kind of did that freehand. It's not like I went in here and measured the distances in between, right? So the scale might not be exactly the same. But what's important is that you label the graph. Labeling your axes is a lot more important than making sure your scale is perfect, all right? A lot of times our scale is not going to be perfect. But as long as the data is labeled, you'll be fine. So that's the difference between a frequency bar chart and a relative frequency. The shape doesn't change. The only thing that changes is the y-axis, right? The vertical axis. The next diagram we'll look, or the next type of chart we'll look at is what's called a Pareto chart, which just simply always puts it in descending order. Puts the highest thing to the left, and then it gets smaller as you go to the right. The reason they do that is to make it easy to identify which one is the highest. All right. In contrast, figure 2.3 shows the relative frequencies of the free types of asphasia in a pie chart. That's generated with a software program called Minitab. We might or might not use that. You know, there's a couple assignments I'll probably use it for, but not a bunch. Right? I'm not as familiar with that as I am with some other statistical software. Excel I'm a lot more familiar with. Right? Note that the pie chart is a circle spanning 360 degrees. And the angle of the pie slice assigned to each class is proportional to the class relative frequency, which is really difficult to do freehand. Unless it happens to be set up 50, 25, 25, right? Then it's easy to create by hand. All right? Now this graph is what's called a Pareto diagram. All it is from highest to lowest. So the one that shows up the most is on the left, to the lowest on the right. And over here, rather than call it the relative frequency, they call it the percent. But it's still the same values, right? This percentage symbol implies divided by 100. That's what it means. That's what the percentage symbol represents. 40 divided by 100 is 0.4. So you notice anomic is slightly above. So notice this chart has the frequency and the relative frequency, which is pretty good, right? It gives us both types of data. And then this line, the black line here, is the cumulative. It's just adding together all of them. That's why right here, notice it hits right at 100%. And that's something we'll get to, right? When we get to our continuous data, we'll see that type of stuff a lot more. All right? So let's go to a summary. Summary of graphical descriptive methods for qualitative data. So let's write these down. Right, a bar graph. The categories or classes of the qualitative variable are represented by bars, where the height of each variable is either the class frequency, class relative frequency, or class percentage. Which I could have done on the other side, right? Over here I could put the frequency. What was it? 10, 7, and 5, right? So to me, I like seeing the relative frequency more, right? This tells me more about it. Doesn't mean a whole lot to say, well, 10 of them had anomic. Well, compared to what? Compared to the rest? So what proportion is that of all the people in the study? A pie chart, which I have a little activity we'll do today and try and create our own pie charts. We'll see who's got the most artistic ability in here of all of us. I saw some funny looks there. It's not a... I'm not very artistic, I'll tell you that right now. Pie chart, the categories, classes, or classes of the qualitative variable are represented by slices of a pie. The size of each slice is proportional to the class relative frequency. And then finally, a Pareto diagram is a form of a bar graph. Something I want you guys to notice is the fact that these bars are not touching each other. You guys see that? How they're separated? That's important, right? A bar graph with these categories or classes of the qualitative variable arranged by height. So this is not a Pareto diagram, right? This is not arranged by height. Okay? So let's look at an example, and then I'll have a class, where you guys have a little activity to do, practice on this stuff. Okay, problem. A group of cardiac physicians, cardiac deals with the heart, right? Heart doctors in Southwest Florida has been studying a new drug designed to reduce blood loss in coronary bypass operations. Of course, that's pretty important, right, when we're talking about the heart. Blood loss data for 114 coronary bypass patients, some who received a dosage of the drug and others who did not, are saved in the blood loss file. So this is a designed experiment, right? There's a control group and a treatment group. Who's our target population here? What do you guys think? Our population of interest, I should say. Same thing.
Bypass patients.
Anybody that needs a coronary bypass is my population of interest. My sample is this 114 coronary bypass patients. Although the drug shows promise in reducing blood loss, the physicians are concerned about possible side effects and complications. So their data set includes not only the qualitative variable drug, which indicates whether or not the patient received the drug, but also the qualitative variable comp, which specifies the type of complication experienced by the patient. So what was a complication? Did they have to redo the surgery, which is probably the worst? Post-op infection, right? Did they get an infection after the operation? Did they have both? Did they have to redo it and get an infection? Or neither? All right? So within this one, there's two different things, right? They either took the drug or not. And in comp, there's 4 outcomes. Redo, infection, both, or neither. All right? So let's look at the data on the next page. So here it is in a chart. So notice their patients were divided up evenly. Now you would expect within those two groups the same amount of men as women, the same amount of people above 70 as below 70, the same amount of people that smoke cigarettes as don't. All that stuff should be relatively the same. Right? Cumulative frequency just means adding them together. So half the people got the drug, half the people did not. Complications. 6 people had both. Which when you consider out of 114, that's really pretty low. Right? It's only 5% of the people. 15 had infection, 79 had nothing, and 14 had to do a redo. So the highest percentage was none, right? Almost 70% of the patients had no problems, no complications. Now you might be asking yourself, well, of these people that had to redo, were they taking the drug or not? Right? You want to put these two things together. Because this doesn't really put them together, right? Right. Oh, here it is, right here. So, did they take the drug or did they not? So, no and yes. Right. So, panel variable is the drug. So, were they getting the drug? No. Look at the people that did not receive the drug. Their amount of complications were a lot lower than the people that did receive the drug. You guys see that? So, of the people that did take the heart drug, the ones that didn't have any complications was a lot lower than the people that did not take the drug. So the drug was obviously giving them complications, right? Both was practically 0 here for the no's. Over here for the yeses, it's up a little bit higher. All right. And then it gets to, let's look at a nice pretty chart for it. What's on here? All right. So rather than do those ones, I want to create a graph with this worksheet here. So I'm going to pull up the document camera. That's basically the discussion of section 2.1. I want you guys to get out a piece of paper and try and answer these questions. And then I'll come up towards the end of class and put the answers and make sure you've got the same thing. And I'll walk around and help if you have any questions. The hair color of 72 students was recorded. Is that a qualitative or a quantitative variable? Qualitative, definitely, right? Non-numerical. The table below summarizes the results. Complete the table below by filling in the missing values and round your answers as directed in the table. So notice the people with red hair isn't there. How do I come up with that number? Do I know the total? All right, 72 and take away the other three categories, right? All right, so I'll give you guys a minute to do that. Fill this chart out, and then I want you to create a pie chart representing it. I want you to use percentages in the pie chart. Label your pie chart with the different classes as well as their corresponding percentages. How many different classes are there? Or categories? 4. All right, so if I was creating a bar chart, I'd have 4 bars. Right? All right, so you guys go ahead and do this. I'll give you a minute. You guys have 5 people with red hair? Right. And then it says round to 2 decimal places. Okay. That same values you guys came up with. Check up here, verify. And notice here it says, be sure to draw your pie chart as accurately as possible. All right. Circle. Dang it, it's 32. And then go ahead and do number 3 as well. Create a relative frequency bar chart. Make sure you label your axes. Yeah, making those shapes exactly the correct size is a little difficult. Really, I like to start with the biggest piece of the proverbial pie and then kind of move down, right? Or use your top
Yeah, I
line.
did use them.
Okay, I was wondering. That's such a perfect circle. Okay. Bar graph. I'll create the bar graph right here. Really good, I'd have those 4 different colored markers. And it says relative frequency, not frequency, relative frequency, which is just the decimal form of the percentages. So this is, a lot of times the shorthand for it will be RF for relative frequency. Then I'll go ahead and just put the frequency over here. And this will be the frequency. Very important. Label your horizontal and vertical axes. Very important. Because what good is it to have the chart up there if it's not labeled? Can you guys have a minute for that? This is the type of stuff you have to do on your homework. Create these type of charts, read these type of charts, interpret. Okay. So if you guys are still working on it, keep working. And that's for RF. Okay. And then this will be, we'll work on this one tomorrow. This has to deal with quantitative data. Notice that's numbers, right? It's not qualitative, it's quantitative. So if I was going to take this into a Pareto diagram, I'd basically just switch the black and the brown, right? And then it'll be in descending order. Create a Pareto. So there's my Pareto chart. Relative frequency and frequency. This is probably typical of a normal population. Most people have brown hair. You could bring in a barber that could probably attest to this, right? Somebody that sees hair all the time. Or a hairstylist that knows the natural color before it got dyed, right? Okay, so let's look at the homework. Okay, notice I have put up here, I've went through and labeled when stuff's going to be due. And make sure when you get to this, you click this Show All button right here. Okay? And for you, I'll help you get into the grade book and all that. Show All, be all on one page, because our review is in a quiz, remember? So notice when I have the quiz due, the Exam 1 review for Chapter 1 and 2 is due 6/11 at 9 a.m. So that's when we're going to take our test next Thursday. So you can work on it all the way up until the exam. All right? The quiz you can do over and over again. All right? There's no set number. But after this date, after this time, you can't do it anymore. Okay? Notice it says 0 of infinite. All right? You can do it over and over again. So that's a good practice test for you. All right? So here's section 2.1. So chapter 1, which we finished today, and section 2.1, which we finished today, are due tomorrow by midnight. All right? Tomorrow, we'll be able to cover 2.2 and 2.3. Those will be due Thursday at midnight. Then we'll cover 2.4 and 2.5 this Thursday. So that'll be due next Monday at midnight, right? Because I like to make it due the day of the class period so you can come in and ask questions. Then we'll cover 2.6 and 2.7 next Monday. It'll be due next Tuesday at midnight. Then we'll cover these next Wednesday. And then there is a day built in, or no, next Tuesday, then it'll be due next Wednesday. Next Wednesday we'll do a review in class. All right, so we'll kind of just talk about everything we've done up to this point. All right, so let me click on this section 2.1. This little thing means there's a prereq. You have to do chapter 1 and score an 80% on it before you can start this assignment. All right, which is the late penalty. So even if you do chapter 1 late, you can still meet the prereq. It's just if you do it late, then you have to get 100 on the assignment so that you can get an 80, right? Because it's a 20% mark off for being late. And of course, I can bypass the prereq because I haven't done chapter 1 yet. I haven't put in all the answers for chapter 1. Now notice here there's 2 videos. How to open a data set from my StatLab and StatCrunch, and how to create a pie chart and a bar chart in StatCrunch. These were created by another instructor here at Eastern. So don't, freak out when you see it and it's not me. All right, it's another instructor who teaches stats all the time. And here it is. So it's a nice video showing you how to import a data set. All right. The second one, it comes up and it gives you a... Oh, there it is. Okay. Sometimes it might come up and say you have to view it on YouTube, which just click the link and it'll send you to YouTube. All right? Because that's where the video's at. So watch this video. She steps through the process of how to create a pie chart and a bar chart in StatCrunch. And it's not very difficult. All right? You click a few things, highlight the data you want, and hit enter. It's not super difficult to create this. And as we've seen, creating a pie chart by hand is not very practical, right? Unless you have a Starbucks cup sitting next to you, and then you can make a nice circle, right? So there's 9 questions. Some of them have 2 parts. Once again, if you get to this, click the middle circle, and then hit Allow Now. And hopefully it pulls it up. There it is right there, loading. Here we go. So complete the table to the right. This is just like the table we just did. I mean, the data is different, but creating the table is exactly the same, right? Frequency versus relative frequency. You have to fill in the blanks, right? And this one has 4 parts. Notice this question has 4 parts remaining on it. There's multiple parts to it. If you're not sure how to do it, you can click View an Example. You can go back to the textbook. You can send me an email through the Ask My Instructor link. Right? So plenty of help in here to help you do your homework. Okay? The nice thing with these is you come in, you can do one problem, maybe you have to run out and do something, you can come back and the problem's already done. Right? It's saved for you. Same thing, frequency stuff. Right? So you got to create, notice this says frequency, not relative frequency. And then when you see this, if you click on it, you can open it in StatCrunch, and the video describes what to do with this type of stuff, all right? Open in StatCrunch, make comma delimited copy, or delimited. That just means how the stuff is separated. How is each observation separated? In here, this is space delimited. All right, there's a space in there. Okay? Then just copy and paste it in. Okay? So you got to go in and count the number of A's in there, right? Notice this doesn't say relative frequency. It just says frequency. How frequent is it? How many times did it appear? Right? A list of college wrestling champions for the years 81 to 2005 is given in the table. Each college has been associated with a particular letter. Probably all from the Midwest, more than likely. And that's where most wrestling's done. Iowa, Iowa State, in that area. I guess ASU had that one kid that only had one leg. Have you guys seen that kid? He's real good. More of the same. Click the icon to view the graphic that summarizes the mall shopper responses. So there it is. there's the responses in a pie chart. So you have to be able to interpret it. Not just give you the answer, right? What type of graph is shown? Okay? Is it a frequency bar graph, a pie chart, a Pareto diagram, or a bar graph? And notice this question has multiple parts. Okay? All right. Let me do a little bit of a introduction into what we're going to cover tomorrow, just to kind of lead you down that path in case you want to get started on it. Let's go back in. Remember, this is how you open your textbook. Go to Multimedia Library, Chapter 2. I'm going to go to Section 2.2. I'm going to go ahead and select all. Once again, you're welcome to look at the PowerPoint. Remember, the PowerPoint is the Reader's Digest version, all right, the synopsis. So that's nice, especially to study, to go through that PowerPoint, all right, when you're studying for your exam. Because it removes all the fluff, right, all the examples and all the other stuff, and really makes you concentrate on the important points. Here's some Java applet, which we haven't talked about these yet. That's in 2.3 and 2.7, so we haven't got that far. All right, we haven't talked about dot plots, histograms, stem and leaf. This is all quantitative stuff. And then finally, there's the multimedia textbook. All right. You guys know the difference between mean and median? What's mean? Average. What's median?
The middle.
The number directly in the middle. Now, in a perfect world, in a normal distribution, the mean and the median are the same. They're equal. Right? But that's not true, especially if we consider the age of all the people in the United States. The baby boomers kind of pull the mean up a little bit. So the median's going to be next to the mean. And we'll see that depending on the relationship between the mean and the median, that tells us how the data is distributed. Whether there's outliers to the left or to the right. Outliers are things that are observations that occur that aren't around the mean, right? Or that aren't normal, right? They're kind of out. You know, maybe like temperature in March, each day was in the 70s, and one day there was a 91. You know, that would be an outlier. That's an example of that. Okay? Yeah, so we'll get in here tomorrow on Wednesday and start with 2.2 and quantitative data. Qualitative, there's not a whole lot of ways to represent it. And a problem with qualitative is that if there's a bunch of categories, your graph can start to get kind of messy. Quantitative is a little bit different. All right, so that's where we'll start tomorrow. Any questions about this stuff? No? All right. Well, thank you, everyone. I'm going to head to my office. I have office hours till 11:30, so if you have a question about it, go ahead and run over there and ask me. JWLA 211P if you need to. Thank you, everyone, and have a wonderful day. Yeah, that's true. Yeah.
Anyway.
No, that's, yeah. Maybe I'll start class off with that tomorrow.
So what you're telling me is, I need to find the kid so in the textbook and kick his ass, because it doesn't have anything to do with the rest of the class.
Well, the textbook's optional,
Right.
but you won't have the code in that old textbook. Yeah, because it runs through this. And that's why I have you guys do this, because it's a little bit cheaper. Now, I wouldn't say get rid of the textbook. It could still be useful. Definitely.
I'll pay for it.
Oh, okay. That's not. And if you follow in the syllabus and go and buy it from them, it's a lot cheaper than the bookstore.
Okay.
Yeah. Yeah, if you go. Oh, yeah. Yeah, and you can look on Amazon, but make sure it's a new code.
Yeah.
Yeah.
I got it for 106 through Amazon.
Oh, did you?
Yeah.
106.
Well, for 106, I bought my code through Amazon.
Oh, not $406. For math 106.
For math 106, no, I
What'd
bought
you
it
pay
for
for it?
like 79
Oh, okay.
or 80. It was only like $10 cheaper.
Yeah, I think from Pearson, we looked at it yesterday, it was 95. The bookstore, I think, wants 130. Don't go to the bookstore. So, But I'd say hold on to that book. It'll still be useful, definitely. All right. Because all the questions in here, if you notice the homework questions, watch, let me pull one up for you. So you go to 2.1, continue. Up in the top right corner, it has a little number up here. And that's the question number in the textbook.
Okay.
See that, 2.1.4? So that's chapter 2, section 1, question 4.
Okay. Sweet.
So, you know, especially if maybe you have questions about this, maybe do the question before it and after it, because it's going to be similar. All right? So,
Cool.
all right?
All
Yeah,
right.
what was your name?
I'm Gary.
Gary. Okay, nice to meet you. London.
You too.
Okay.
Yeah, sorry about yesterday. It was a rough weekend.
Oh, yeah?
I'm a bartender over at Kelly's.
Oh,
I usually get home about 4 o'clock Sunday morning and back up and at church at 8.
But you guys aren't open Sundays?
No. Just question.
Yes. Formulas. Are they, do you have to memorize them, or
No,
you
I
have the formula sheets?
Yeah.
That they
Watch, I'll show you.
I pulled them up. I printed them.
Oh, did you? Okay, yeah.
But I didn't know if.
No, I'll give them to you.
memorized.
See, and I can't let you bring in your own formula sheet.
No, I printed them up.
Yeah, yeah, but this, yeah, I'll give them to you.
Okay. I was just wondering.
Yeah, I would not make you, expect you to memorize those. Not at all.
Just wondering.
Okay, thank you.
Have a good day.
Yep.